Hi everyone. So what the derivative basically is it's a rate of change of something. Now you may be thinking, hey Ryan, that sounds kind of familiar. In fact, it sounds an awful lot like slope. And you would actually be right. Because what the derivative basically is it's a slope at a particular point of a function. So here I have different notations for derivative. I have f prime of x, which is very popular. I have dy over dx, which is change y over change in x, which is another reference to slope. I have d sub x, which, honestly speaking, I've never seen used in my calculus class. But if you want to learn it, by all means, go ahead. And I also have this equation, which should hopefully look familiar to you by this point, because this is the equation for tangent line. So, you should always recognize that the tangent line of a point in a function is the same thing as the slope of that point in the same function. Okay, so you may have noticed that I have this other equation that's this derivative of a point. And you'll be thinking, Ryan, if the derivative is a slope at a particular point, why do I have these two different equations? So the answer to that is this. What this basically is this is like the general form of the derivative. If I have a function f of x, and then I solved for that function, or I solved, quote unquote, by getting rid of the change in x, and finding the limit of that function, then I would get this new function, f prime of x. And f prime of x will let me find the derivative at any point by just plugging in for x. However, if I don't want to do all that, if I don't want to find the general function of the derivative, then I can just go to this equation. And if I wanted to find the derivative at a particular point a, then I can just use the original function f of x, and then just use f of a. However, both equations use basically the same principle. They both try to find the slope by using 2 points that are close to each other as possible. And you may be asking why. Well, if I have a line like this, then it's pretty easy to remember from geometry. At the slope on this line is the change in y over change in x between any 2 points, and I can choose literally the points that are furthest away from each other as we can possibly see, and I would get the same slope. So I would get the same derivative at any point. However, if I have something a bit more complex, like this function, then suddenly I want my points to be as close to each other as possible. Because if I wanted to find the derivative of this point, or the slope at this particular point, I don't want to find the slope between this point and this point. Because, well, there's a pretty obvious change in the rate of change. Like, for example, the tangent line here, it looks to be like, it's more like this. It's increasing gradually. But the tangent line here is like, whoa. So you get the general idea, hopefully. So I want to find the slope between 2 points who are as close to each other as I can possibly get, to be as accurate as possible in the slope. Okay, so let's look at a couple differentiable and not differentiable functions. So here I have one function. It has no holes, no asymptotes, which might be hard to see, but there are no asymptotes. And it does continue off indefinitely into outer space, let's say. So essentially, this function is differentiable over its entire domain of all real numbers. And ideally, hopefully, after a full year of calculus, it should be really easy to find the derivative of this function. So let's look at another function, though. It looks quite the same, but I just introduced a new hole into it. So can it be differentiable everywhere? The answer is no. Because the derivative is an instantaneous rate of change, or the slope at a particular point. Consequently, the point has to exist. So this function is differentiable everywhere except for this point. Let's look at another function. Okay. So now I have a function which has a vertical asymptote. So I could find the derivative anywhere except for here. Why? Because the tangent slope here would literally go straight up and down. And the equation for that tangent line is undefined. So no, we can't find the derivative at that point. But how about this point? Right here. Could I find the derivative at that particular point? The answer is no. Because, well, the idea of a derivative, one of the ideas, is something called local linearity. If I were to zoom in as close as possible to that line, it should look straight, because that's the tangent line. However, if I zoom in infinitely to that point, it'll still look exactly the same as it does like this. And if you don't believe me, you can try it out for yourself on your graphing calculator. Okay, so just to sum everything up. Whoops. Okay, So this is what you should remember from this lesson. You should be able to recall or recognize different notations for derivative. That should actually be quite easy. You should also be able to remember and use the equation for the tangent line. You should also recognize that derivative of a function at a point is the same thing as a tangent line at that point. Okay, you should also memorize and be able to use this equation for a derivative at a particular point, while foregoing the actual general equation for the derivative. You should also be able to tell if a function is differentiable, and you can usually tell if within the specific domain that you're looking at, if it has no holes, no vertical asymptotes, and if it has local linearity. Alright, thank you, have a nice day, and hope calculus is being awesome.